ಬನ್ನಿ ಹಿಂದ್ಗಡೆ ಹೋಗಿ ತೊಂದ್ರೆನಾ? ಯಾಕಂದ್ರೆ ಆ ಕಡೆ ವೈರ್ ಹಾಕ್ಬಿಟ್ಟು
ಸೊ ಶುರು ಮಾಡೋಣ ಸರ್.
ಹಾ ಖಂಡಿತ. ಓಕೆ, ಶುರು ಮಾಡಿ.
So I welcome to today's resource person Dr. P. Nagaraju sir for this webinar class. So I welcome to you sir.
Oh, thank you sir, thank you.
So I welcome to our academic managing director A.V. Basaraju sir and our academic CEO sir Dr. Ramesh A.M. Ramesh sir and all the attendees. I welcome to one and all. I welcome to you sir and one and all.
Okay sir, thank you, thank you. So let's start now.
No sir, ನಾನು ನಿಮ್ಮ ಬಗ್ಗೆ ಒಂದು 2 ನಿಮಿಷದ ಒಂದು ಇಂಟ್ರೊಡಕ್ಷನ್.
ಆಯ್ತು, ಏನ್ ಹೇಳಿದೀರ ಹಿಂದೆನೆ ಬಿಡಿ, ಎಂತದ್ದೇನು ನಾಗರಾಜ್ ಅಂತ ಹೇಳಿ ಸಾಕು.
ಇರ್ಲಿ ಸರ್. ಡಾಕ್ಟರ್ ಪಿ ನಾಗರಾಜ್ ಸರ್, ರಿಟೈರ್ಡ್ ಅಸೋಸಿಯೇಟ್ ಪ್ರೊಫೆಸರ್ ಆಫ್ ಫಿಸಿಕ್ಸ್ ಅಂಡ್ ವೈಸ್ ಪ್ರಿನ್ಸಿಪಲ್ in Vijay College, Bangalore. So currently he is working as a professor of physics, PG department of physics, the National College, Autonomous Jayanagar, Bangalore. Sir got a PhD in Bangalore University in 1993 and having the 44 years teaching experience, and also he served in many colleges: JSS College, Mysore, Sathya Sai College, Whitefield, Bangalore, Vijay College, Bangalore, GVS College, Anakal, Bengaluru, and Indian Academy Degree College, Bengaluru. And sir have 32 research experience and also have administrative experience in Vijay College, Bengaluru. And is working as a HOD of physics in 1998 to 2007 and working as a coordinator of MSc Physics April 2012 to September 2013, and also working as a vice principal September 2013 to November 2014, and also working as a AOE chairman Bangalore University 2013 to 2014 and working as a principal February 2015, August 2015 GVS College, Anakal, Bengaluru, and also working as a professor and head in August 2015 to December 2018 Indian Academy Degree College. Also working as a control of examination October 2016 to December 2020 Indian Academic Degree College. And sir published 9 papers, national and international journals, and also attend a number of conferences like national and international conferences out of 35 by 5, and also workshops and seminars attend out of 25 10. And sir visited in outskirts like country Germany, Italy, Switzerland, and USA. And also he guidance PhD to one Bangalore University in May 2003 and one MPhil guidance for Annamalai University, and author of books also on PUC first and second year CET Karnataka member of 7th standard textbook 2014 Government of Karnataka, and member of scientific bodies and the executive committee in Indian Physics Association IPA 1994 to 1996, in Bangalore University First Grade College Physics Teacher Forum President 2002 to 2008, also in Indian Association of Physics Teacher IAPT President Regional Council 2007 to 2016, and also sir worked as a examiner and paper setter in 2010s BEB, NMR, NMK Harvey College, Christ and Jain Universities of St. Joseph College, National College, Presidency University, and Christo, Jain City University, PUA University. Okay, thank you. Over to you, sir.
Oh, yes sir. Okay sir, thank you. So thank you for the opportunity given to me to interact with second year PUC students right now, because this topic is in the second year PUC syllabus, wave optics. Anyway, I thank all the members of KSTA, Karnataka Science and Technology Academy, especially the CEO, Dr. Ramesh, and also the chairman. And I welcome all the students to interact with me in case if they have any clarification. For the first, I will just introduce the topic of wave optics. Afterwards, if you have any doubts or clarification or comments, definitely you are welcome to give your comments. Anyway, I wish you all the best in your career. With that, let me come to the topic of wave optics. Dear students, you know that the optics can be classified into two categories or two branches. One is ray optics, and ray optics deals with the rectilinear propagation of light. That means straight line property of light. There we discuss about especially the reflection and refraction phenomena. There are other things too, but anyway, I am now concentrating on wave optics, which is very much there in your syllabus. And this wave optics actually deals with both the reflection, refraction, and then interaction of light on matter, and particularly the propagation and the properties of light. So let me just start with, you know that the wave optics for the first time, uh, anyway, first the corpuscular model was given by Descartes in the year 1637 and actually derived Snell's law. You know that the Snell's law is the ratio of the sine of the angle of incidence to the sine of the angle of refraction for a given pair of media and for a given wavelength of light. In other words, in mathematical form, we write that in general, we write 1 and 2 is equal to sine I by sine R. Or in other words, absolute refractive index is written as n is equal to sine I by sine R. And in terms of the velocities of light, the refractive index is n is equal to c by v, where c is the velocity of light in air or free space, and v is the velocity of light in the given medium. So why do we have the two definitions? In fact, n is equal to c by v is the correct definition. In the sense, Snell's law does not hold good, especially when the light ray is in the direction of the normal. You know that, like actually I have told you that n is equal to sine I by sine R. If the angle of incidence is 0, the angle of refraction is also 0. In that case, it becomes 0 by 0. 0 by 0 is indeterminate, but the refractive index is not indeterminate. It has a definite value, and Snell's law has its own limitation. I think that you must have seen some old question papers, and in the question paper, it says that Snell's law does not hold good when the angle of incidence is 0. That means the Snell's law has its own limitation, and the limitation is if the light ray is in the direction of the normal, it will not be valid. And therefore, in general, we define the refractive index in terms of the velocity of light, that is n is equal to c by v. Again, I repeat, c is the velocity of light in air or vacuum, that is 3 into 10 raised to 8, whereas v is the velocity of light in the given medium. It may be water, glass, diamond, or anything. Anyway, this Descartes model explained the reflection and refraction too, including interference. This corpuscular model of light was further developed by Sir Isaac Newton in the year 1672. And this is also called Newton's corpuscular theory of light. According to Newton, the light particles are emitted from a luminous body. When once the light particles are emitted, they travel along a straight line with enormous speed. And therefore, these light particles can be compared to that of the bullets fired from the gun. You know that to some extent, the bullets, when once they are fired, they travel along a straight line. It is in that way, these corpuscles can be compared to that of the bullets. So anyway, these corpuscles, when they are emitted from a luminous body, they travel along a straight line with enormous speed. Of course, this corpuscular model explained the phenomenon of reflection satisfactorily. In order to explain the phenomenon of refraction, it demanded that the velocity or the speed of light is greater in denser medium than that of the rarer medium. If you look into some old question paper, you will find that according to corpuscular theory, the velocity of light, something like four options, is greater in denser medium than that of the rarer medium, greater in rarer medium than that of the denser medium. It is equal in both the rarer and the denser medium. Like this, you have the options. And remember, according to Newton's corpuscular theory of light, the velocity or the speed of light is greater in denser medium than that of the rarer medium. Anyway, Newton's corpuscular theory of light could not explain simultaneously the reflection and refraction phenomena. And at the same time, it could not explain the phenomenon of interference, diffraction, including polarization. And thus, the other model, that is actually the wave model, or in other words, you may call it as wave theory of light. This wave theory of light was established by Huygens. And in other words, we call it as Huygens wave theory of light. This Huygens wave theory of light was introduced in the year 1678. And he suggested that, that when once the light particles are emitted from a luminous body, they travel in the form of a wave. And the wave is basically due to the disturbance. So when the disturbance is created in a medium, the wave is propagated, and the propagation or the disturbance propagated in the medium is called the wave motion. So anyway, coming back to our light particles, these particles are emitted from a luminous body. When once they are emitted from a luminous body, they travel in the form of a wave and not in the form of like a straight line. And this Huygens wave theory assumed that the wave is longitudinal in nature. You know that light waves are longitudinal in nature, in the sense this was the theory suggested by Huygens. And according to Huygens wave theory of light, the speed or the velocity of light is greater in rarer medium than that of the denser medium. Of course, this was experimentally verified by Foucault. That was in the year 1850. Anyway, we know that the velocity of light is greater in rarer medium than that of the denser medium. But one important thing to be noticed in this Huygens wave theory of light, I already told you that it is longitudinal in nature according to Huygens wave theory. Further, he assumed that a medium is required for the propagation of the wave, and that medium he called that as ether. According to Huygens wave theory, ether fills the empty space as well as the material medium. In other words, we call it as all-pervading medium. That means it is everywhere. And this, of course, the wave theory of light explained the phenomenon of reflection and refraction simultaneously. And later on, this longitudinal wave nature of light, what was suggested by Huygens, was extended by Thomas Young in the year 1800 to explain the phenomenon of interference. And you know that Thomas Young, it is also called the Young's double slit experiment, and he conducted the experiment by allowing a fine beam of sunlight into the dark room. I am not going for the experimental details of the Thomas Young's double slit experiment, and in fact, you must have already studied it. Anyway, I will go for the mathematical derivation of it. But uh, the Young's interference experiment was the first strong supportive argument in favor of the wave theory of light. No doubt, the longitudinal wave nature of light was able to explain even the phenomenon of diffraction. But to explain the phenomenon of polarization, it failed. In order to explain the phenomenon of polarization, John Fresnel, that was in the year 1802, suggested that light waves are transverse in nature. So remember that light waves are not longitudinal in nature, they are transverse in nature. That means the propagation of the light particles are in a direction perpendicular to the vibration is perpendicular to the propagation of the energy. So anyway, this ether medium, still it is inconclusive medium in the sense later on it was proved that the non-existence of the ether medium. Anyway, I am not going for how to prove the non-existence of the ether medium by Michelson-Morley experiment. In addition to that, we have another major theory, that is the electromagnetic wave theory of light. This electromagnetic wave theory of light was introduced in the year 1864 by Maxwell, Clerk Maxwell. According to uh, electromagnetic wave theory of light, electric and magnetic fields oscillate in a direction perpendicular to the propagation of the electromagnetic wave. That means the electric and the magnetic displacements are at right angles to each other, and the electromagnetic wave is in a direction perpendicular to these two. And he suggested that the light wave is an electromagnetic wave, and the velocity of light in free space or in vacuum, it is equal to 3 into 10 raised to 8 meter per second. It is same as the velocity of or the speed of an electromagnetic wave. And Maxwell also derived four basic equations. We call that equations as number one is divergence D is equal to rho, which I have given in the bottom. And in other words, you can also write it as divergence E is equal to rho by epsilon naught, where rho is the density and epsilon naught is the permittivity of free space. Divergence B is equal to 0, where B is the magnetic field and E is the electric field. So then curl E is equal to minus del B by del T, and curl E equals minus del B by del T, and curl B is equal to mu naught times J plus epsilon naught del E by del T, where mu naught is the permeability of free space. You know that the value of the permeability of free space is 4 pi into 10 raised to minus 7 Henry per meter, whereas the value of epsilon naught, that is the permittivity of free space, is 8.854 into 10 raised to minus 12 Farad per meter. And this epsilon naught, what you have got it in the, J is the current density, and plus epsilon naught delta E by delta T. That epsilon naught into delta E by delta T, in other words, you may even write it as del D by del T. That is the dielectric displacement. It was Maxwell who introduced the concept of dielectric displacement current. So with these four equations, he was able to get the expression for the velocity of light in free space, that is C equals 1 over square root of mu naught epsilon naught, and that is equal to It is 2.9779 into 10 raised to 8 meter per second, and approximately we write it as 3 into 10 raised to 8 meter per second. So the electromagnetic wave theory, thus it explained the phenomenon of reflection, refraction, interference, diffraction, but it could not explain especially the black body radiation and of course the photoelectric effect. There were some drawbacks to explain the photoelectric effect, black body radiation, and because of that the other theory was introduced. Anyway, I am not going to discuss more about the electromagnetic wave theory. Electromagnetic wave theory is also there as a separate chapter. There you will study. Here in this context, I have just introduced different theories like the particle nature, that is Newton's corpuscular theory, Huygens wave theory, and also the electromagnetic wave theory. Anyway, there were some drawbacks, and therefore it was Max Planck in the year 1900 introduced altogether a new theory, and that new theory is called the quantum theory of light. This quantum theory of light explained the black body spectrum successfully. Not only that, it was used to explain the phenomenon of photoelectric effect and then specific heat of solids, Compton effect, etc. And you know, the concept of Planck's quantum theory is the discrete packets of energy or quanta of energy is written as E is equal to nh nu or nhf. Here I have used the symbol f to denote the frequency, where n takes the value 0, 1, 2, 3, etc. H is the Planck's constant, and that is 6.6025 into 10 raised to minus 34 joule second, and f is the frequency. In place of f, you can even write it as nu. Planck stated that the energy of the quantum is either completely absorbed or emitted in an optical process. A quantum, later on it was called a photon, and the name photon was given by George Newton Lewis in the year 1926. So now either we can call it as quantum or photon. And remember, this photon or the quantum cannot be broken, or there is no fractional photon. For example, let us consider a red bulb of 40 watt, which is emitting red photons. How do we calculate the wavelength of the rather, let us say the wavelength of the red photon is approximately 700 Newton meter. Sorry, not Newton meter, nanometer, 700 nanometer. How to calculate the energy of this red photon? We use this formula like E is equal to HF E or HC by lambda, because you know F is equal to C by lambda or mu is equal to C by lambda. Anyway, in this, it clubs like crowded, and you have to take it HF is equal to HC by lambda separately, and E, in order to calculate the energy, we have H equals 6.625, right, 10 raised to minus 34 into 3 into 10 raised to 8 over 700 into 10 raised to minus 9, because 700 nanometer, when you calculate it, approximately it comes to be 3 into 10 raised to minus 19 joule. The number of photons emitted by a 40 watt bulb, you can write it as P is equal to NSC by lambda, or P is equal to NE. Therefore, you can even write it as N is equal to P by E. Let us say the red bulb of wattage is 40 watt, and the energy is 3 into 10 raised to minus 19, which I have shown how to calculate it. And the number of photons which we are getting on simplification of this comes to be 10 raised to 20. So 10 raised to 20 photons are emitted per second. So in view of the fact that the number of photons emitted per second is very large, we not able to see these nature or the discrete nature of radiation. In other words, Because the wavelength of the light is very small, it is of the order of, assuming that it is 600 to 700 nanometer. Actually, the visible radiation is 400 to 800 nanometer. Whatever it is, approximately, if we take it as 600 10 raised to minus 9 or 6 into 10 raised to minus 7 meter, which is so small, naturally, we are not able to see it. And that's how the quantum theory of radiation brought in the corpuscular aspect of light, even though the what is that called quantum theory of light explained the phenomenon of black body radiation, photoelectric effect, specific heat of solid, Compton effect, but it failed to explain the theories like uh, interference, diffraction, polarization. And that is why we have both the wave nature, rather wave particle duality, or in other words, we call it as de Broglie wave. Anyway, I'm not going for the de Broglie wave concept. With this, let me now go for the Huygens principle. What is this Huygens principle? Under the Huygens principle, first you have to understand the meaning of a wavefront. The definition of the wavefront is the locus of all the points which are in the same phase. The meaning of the phase is the state of vibration. And if there is a difference in time between the two vibrating particles, we call it as the phase difference. I will give you the mathematical expression for the phase difference and the path difference in another slide. And in the wavefront, yes, you can just think of that, how to understand the concept of the wavefront. Just imagine that you drop a small stone, which we call it as a pebble, at a small pond. If you think that there is a small pond, and small pond means you can't go for a big pond or a lake. Let us say you have a small pond, and in a small pond, provided the water is there, if you drop a stone or a pebble, a small one, and you will find that at the point where the pebble is dropped, the water molecules will rise up, and the same water molecules which are raised up will fall back, and they constitute, then that uh, point where the stone is dropped forms a wave around that stone. And those water molecules which are raised up will fall back. And when once they fall back, they make the other water molecules to rise up. Like this, the waves are produced over the entire pond, and these waves will reach the end of the pond. That you also call it as the wave propagation or wave motion. Anyway, like that, if you have a disturbance, a small disturbance means then waves are produced. And if the point source is at a small distance, and then you call that as the spherical wavefront. The spherical wavefront is shown in this diagram. You see that here you have a point source of light, and then assume that these particles are actually disturbed, and they are it in the form of a circular one. The envelope of these outer circles will be drawn, and that constitute the secondary wavelets. That means the primary wavefront forms the secondary wavelength. This is what the basic principle of the Huygens wave theory. In fact, in order to understand the Huygens wave theory or the Huygens wave principle, it takes at least 30 to 40 minutes. But anyway, I have just introduced the concept without going into the details of how we get it. Then suppose we have the source at a large distance, the point is at a large distance from the source. A small portion of the spherical wave can be approximated by a plane wave. That means the observer and the source are at large distances. You see that here, this is the primary wavefront, and this primary wavefront leads to new position of wavefront after some time. And these new wavefronts, we call them as the secondary wavefront. or secondary wavelet. And this is what you are able to see both the plane wave front as well as the spherical wave front in the same diagram. So this diagram shows you the first one A will give you the plane wave front, and the second one B will show you the spherical wave front. So this is what that means. Plane wave means the source is at a larger distance, and the spherical wave front means the source is at a smaller distance. So in addition to this plane wave front as well as the spherical wave front, we may also have one more, and that is nothing but the cylindrical wave front. Yes. And you should also know about the coherent and the incoherent waves. The coherent waves, see, the sources are the waves which have the same amplitude or nearly equal amplitude, same phase or a constant phase difference between them. Same phase, PHASE, same phase or a constant phase difference between them. In addition to that, we have the same wavelength and the frequency. Then, if these waves have the same amplitude or nearly equal amplitude, same phase or a constant phase difference between them, and same wavelength, then the waves are called the coherent waves. I hope you have already seen that how only when we have the coherent waves, we are able to get the constructive and destructive interference. So the constructive interference, I will again tell you what exactly we mean by the constructive and the destructive inference. So if the phase is not the same or nearly equal amplitude or not, if these conditions are not satisfied, then we call them as incoherent waves. By an incoherent waves, we will not be able to get the interference pattern. Interference, in other words, you may even call it as the superposition of waves. That means when two or more light waves of same amplitude or nearly equal amplitude superpose or overlap with one another, the energy will be distributed and it forms what we call them as bright and dark fringes. Here I will give you when do we get the bright fringes and when do we can get the dark fringes. Anyway, the wave propagation, which you can write it as y1 is equal to a sine omega t. It is omega, not w. A is the amplitude and omega is the angular frequency at any instant of time. Let us have another wave y2 is equal to a sine omega t. Of course, in the NCERT book, it is given as y1 is equal to a cos omega t and y2 is equal to a cos omega t. But I have taken a sine omega t and a sine omega t in order to show you that not necessarily you have to take a cos omega t. You can take even sine omega t. You know that between sine theta and cos theta, there is a phase difference of 90 degree. Suppose these two waves are superposed, or in other words, overlap with one another, we will have the resultant displacement. And remember, y1 is the displacement of the vibrating particle for 1, and y2 is the displacement of the vibrating particle for 2. So y is equal to y1 plus y2. And if you add these two together, because they have the same amplitude and same angular frequency, there is no phase difference between them. And that is why you will get that 2a sine omega t. So next, how do we define the amplitude? There is a difference between the displacement and the amplitude. The maximum displacement of the vibrating particle is called the amplitude. So basically, the amplitude is nothing but the displacement, but maximum displacement. And we also know that the intensity is directly proportional to square of the amplitude. If you take it as 2a is the resultant amplitude, and if you take the intensity, that intensity is nothing but 4I0. That means you may write it as 4a square, and a square is taken as I0. 4I0. On the other hand, suppose we have, let us say, y1 is equal to a sin omega t, y2 is equal to a sin omega t plus phi, where phi is the phase difference. And I told you in the beginning that there is a relation between the phase difference and the path difference. The relation between the phase difference and the path difference can be written as phi is equal to 2 pi by lambda into delta t, delta. Or even you can also write it as delta phi is equal to 2 pi by lambda into delta x. But anyway, here I have used phi to denote the phase, and path difference is denoted by delta. We can even write it as delta phi is equal to 2 pi by lambda into delta x. Then suppose you want to add these two waves, in the sense superposition of these two waves is y1 and y2 equals a sin omega t plus phi. y1 is equal to, sorry, y is equal to y1 plus y2. You see that here I am adding that a sin, oh sorry, omega t is missing in this, and you have to put omega t there. It is a sin omega t, I didn't notice it, and a sin omega t plus phi. And what is that? So you have to expand this sin omega t plus phi. So you know that sin of a plus b is equal to sin a cos b plus cos a sin b. Like that, sin omega t cos phi plus cos omega t sin phi. And you take and simplify that. If you simplify that, you will get it as 2a cos phi by 2. And sin omega 1 plus cos phi you get, and that you will write it as 2 cos, and you will have to take the common factor. Then it is sin omega t plus phi by 2. So in other words, it is this 2a cos phi by 2 gives you the amplitude. That is the resultant amplitude. And this resultant amplitude is nothing but 4 I naught cos squared phi by 2. So where phi is the phase difference, and if phi is equal to 0, 2 pi, 4 pi, 6 pi, etc. In other words, in general, we can write it as plus or minus 2n pi, where n is equal to 0. Suppose I take n is equal to 0, then you get it as phi is equal to 0. Suppose I take n is equal to 1, then you get it as phi is equal to 2 pi. So in general, we can write that phi is equal to plus or minus 2n pi gives the constructive interference. And similarly, if the phase difference is an odd multiple like 2n plus 1 into pi, so again, if you take n is equal to 0, it becomes pi, and odd. And if n is equal to 1, it becomes 3 pi. That means if the phase difference is pi plus or minus, even here also it should be plus or minus, it is pi, 3 pi, 5 pi, etc. It leads to destructive interference. So this constructive and destructive interference leads to the bright and the dark bands. So this is what we have a major derivation in even from your point of view of your examination is theory of fringes or expression for the fringe width. What is that? In the textbook, yeah, the diagram is given like this, and in the textbook it is given as from the what is that, Pythagoras theorem. It has been divided the expression for the fringe width. But anyway, here I am using one more relation, just the trigonometry. I write that if you look at the diagram, tan theta, let us say QOP in this diagram is a right angle triangle. In this right angle triangle, I am writing that tan theta is equal to PO by OQ or QO, which you can write it as tan theta is equal to Y by D. And let us say I take the triangle. Of course, in the diagram, it may not look like the exact right angle triangle. Assume that S1, S2, and where I have got, you can use A. I have not written A here. S1, S2, A. Then it comes to be S2, A is actually the path difference. So in this right angle triangle, you can write that, yeah, if you write sine theta is equal to S2A by D or S1, S2. And yeah, this is what I have used here. I think I will come back to what I have orally told you. I have written it here. Tan theta is equal to y by d. Sin theta is equal to S2a by d. Therefore, one more assumption is made here. Tan theta is nearly equal to sin theta. And remember, you have proved in trigonometry, when limit theta tends to 0, sin theta by theta is equal to 1. Similarly, tan theta by theta is equal to 1. That is taken only when theta is very small. That means under the limiting condition, theta tends to 0. So if tan theta is equal to sin theta, in that case we write S2a by d is equal to y by d, and S2a is equal to yd, just cross multiplication, y small d by capital D, which gives you the path difference. Suppose the path difference is equal to an integral multiple of lambda, or it is an even multiple of lambda by 2, it leads to bright fringes or bright bands. On the other hand, if the path difference is equal to, oh, here 2 is missing. Please write down here 2n plus 1 into lambda by 2. I think I thought that 2 is there, but 2 is now, I am seeing that it is not there. So please write down there S2a is equal to 2n plus 1 into lambda by 2. It leads to dark fringes or dark bands. And anyway, n is equal to 0, 1, 2, 3, etc. Either you take an integral multiple of lambda or even multiple of lambda by 2. Here n takes the value 0, 1, 2, 3, etc. Similarly, here in the dark fringes or dark. So after simplification, suppose you write that S2a, then you get the expression for beta, and beta is equal to lambda d by d, and where beta is the bandwidth, or you may even call it as the fringe width. Distance between any two consecutive bright fringes or the distance between any two consecutive dark fringes is called the fringe width. And remember, the interfere fringes are equal bright fringes and equal dark fringes. In other words, the width of a bright fringe is equal to the width of a dark fringe. Later on, you will be studying about the diffraction bands or diffraction fringes, but the diffraction bands are not of same width and same darkness. In fact, when we come to diffraction phenomena or diffraction pattern, there we say that the central maximum is flanked by alternate dark and bright bands of decreasing intensity and decreasing width. Anyway, there is no time for discussing even the diffraction pattern also. The organizers have told me to take up some multiple choice questions. Therefore, I will now move on to the multiple choice questions. You see that I have already told you that maybe if you look into some old question paper, I told you about according to Newton corpuscular theory of light, the velocity of light, I told you that is actually greater in denser medium than that of the rarer medium. But the choices would be given as greater in denser medium than that of the rarer medium, or greater in rarer medium than that of the denser medium. The velocity of light in rarer as well as in the denser medium is the same, or something else can be given. And you remember that it is greater in denser medium than that of the rarer medium, even though the velocity of light is greater in rarer medium. That's what I told you in connection with the Huygens wave theory. The Huygens wave theory suggested that the velocity of light is greater in rarer medium than that of the denser medium. And that is what we have on today. Yes, coming to some question here. Question number 1, which I have given here is, how is the interference pattern in Young's double slit experiment affected if the sodium, what is that? Sodium, nothing but yellow light, is replaced by red light of the same intensity. Anyway, for this interference pattern, intensity, it is only for vision we have to give some intensity, brightness. intensity means brightness, but it is nothing to do with the fringe width. And the four choices are given. What are the four choices? The fringes will vanish. Next one is the fringe will become brighter. Next is the fringe width will decrease. And the last one is the fringe width will increase. What is that you have? Yeah, right now we have got that fringe width is beta is equal to lambda d by d, where lambda is the wavelength, capital D is the distance between the coherent slits. What you have got in the theory of fringes or the expression for the fringe width, S1, S2, nothing but the coherent slits. In fact, I didn't explain. Actually, we have a source, and from that source, we get both the primary and the secondary wavelets, and those waves reach the slits S1 and S2. Again, the waves coming out of the slits S1 and S2 would be able to reach the point P on the screen. So that's why, anyway, I didn't go for the detailed explanation of it. You have already got the explanation, or you will look into that. That's why I have just only given you the flavor of it rather than going into the interference, double slit experiment, and also the theory. Because you know that to explain the double slit experiment and also to get the expression for the fringe width, it takes almost a period. Yeah, what you have got in the textbook, I tell you again, in the form of Pythagoras theorem, but here I have shown in the form of trigonometric relation like tan theta and sin theta. Anyway, coming back to this, beta is equal to lambda d by d, where lambda, you know, for example, Young's double slit experiment, if the sodium light is replaced by red light, for red sodium, approximately you can take it as 600 nanometer, that is yellow, and for red you can take approximately 800. You may take from 700 to 800, or you may even take it as 750 nanometer. Anyway, the wavelength is more, and in the numerator of the fringe width, you have yeah, there is a question like state the reason why. I will come to it later. Anyway, the lambda is more, and since the lambda wavelength is more, the fringe width will increase. So the choice, the correct choice for the first question is the last one, that is D, fringe width will increase. Let me now move on to the question number 2. That question number 2 is, in Young's double slit experiment, if the distance between the slit and the screen is doubled and the separation between the slits is reduced to half, the fringe width is. So what happens to the fringe width in case? Yeah, like again, you have to go back to the same expression, that is beta is equal to lambda d by d. And capital D is in the numerator, and it says that the distance between the slits and the screen is doubled. That becomes 2d. You may even write it as lambda d dash by small d dash. D dash d capital D dash is 2d and small d dash is d by 2. So if you simplify that, you will get it as 4 into lambda d by d. That means what is the answer for this question? The question is, anyway, becomes 4 times. Second option, that is B option, is the correct option for the question number 2. Again, I repeat, in Young's double slit experiment, if the distance between the slit and the screen is doubled and the separation between the slits is reduced to half, then the fringe width becomes 4 times. Let me now move on to question number 3. Question number 3 says that what happens if the monochromatic light is used in Young's double slit experiment is replaced by white light? But for the definition of the monochromatic, some of you may say that it is a light of single color. But remember that monochromatic means light of a single wavelength. For example, if you look at a yellow color, it is a single color, but there are two wavelengths, 589.3 and 589.6 nanometer. That is why even though there is a single color, there may be several wavelengths. The minimum is in respect of yellow. Anyway, yellow is taken as a monochromatic source in the laboratory for doing some experiments, but the correct monochromatic source can be thought of as the laser source. Only laser source is a monochromatic. Let me repeat, monochromatic light means light of a single wavelength. So in this question, Young's double slit experiment is replaced by a white light. White light means there are several, and yeah, let me come back to that question. Here you have many options, like you come to the third option, that is C. I think C is missing here. First one is A, second one is B, and third one is C, but A, B, C are missing in, maybe I am transferring from Word to this, somewhere it is missing. I could not notice it. Anyway, the third one, you can remember, only the central fringe is white and all the other fringes are colored. So this is the option for the question number 3. Let me move on to question number 4. Question number 4 says, what will happen if one of the slits in Young's double slit experiment is covered with a cellophane paper which absorbs a fraction of the intensity of light from the slit? Yes, anyway, you are going to study that in diffraction. There you will have a single slit. In fact, single slit that leads to what we call it as, there are two types. One is Fresnel diffraction. The other one is Fraunhofer diffraction. You are going to study about the Fraunhofer diffraction at a single slit. That means to say that if you have a single slit, it leads to the diffraction pattern. So the diffraction pattern is again here A, B, C. The C is missing here. Sorry, here only I am noticing it. The bright fringes will become less bright. Oh no, because actually the yes, this is the choice for this C. C is missing. The bright fringe C is missing in the sense the number C is not there, but the sentence is there. The bright fringes will become less bright and the dark fringes will not be completely dark. In other words, you may say that will be like what I told you in the beginning, that central bright fringe is what is that, flanked by alternate dark and bright fringes. So third option is the correct one for question number 4. Coming to question number 5, and this question 5 says that in Young's double slit experiment, if the slit widths are in the ratio of 1 is to, in the ratio, because 1 is to 2 there, the ratio of the intensity at maximum, at minimum and maxima will be. For this, you may write like I maximum over I minimum. That is what normally you do. Don't forget to reverse it. That means first you can write I maximum over I minimum. I think better you write down I maximum over I minimum equals. I told you in the beginning itself, intensity is directly proportional to square of the amplitude. And in the superposition principle, the two waves superpose with one another and resulting in alternate dark and bright bands. That's what I told you in connection with already interference. So we can write I maximum over I minimum is equal to A1 plus A2 whole square whole over A1 minus A2 whole square. Remember, it is given A1 by A2 is equal to 1 by 2. That means you can write A2 is equal to 2A1. So let me come back to that. In place of A1, you write A1 as it is, and A2 you can write it as 2A1. That means A1 plus 2A1 whole square whole over A1 minus 2A1 whole square. A1 plus 2A1 becomes 3A1 whole square, and in the denominator A1 minus 2A1 becomes minus A1 whole square. Anyway, when you square it, it becomes positive. It comes to be A1 cancels, and therefore you get it as 3 square is 9, 9 by 1. But the question says minimum and maximum. Because it is minimum and maximum, you will have to take it as it is 1:9. That is the fourth option. For question number 5, fourth option, that is 1:9. I hope you got it, how you can simplify. Remember, I maximum over I minimum, or if you want to write it in the beginning itself, I minimum over I maximum, then you write it as A1 minus A2 whole square over A1 plus A2 whole square. In fact, hardly you may get about 50 to 60 seconds, means 1 minute for each question. And therefore, you should not waste your time in calculating neatly. You can roughly calculate, and you can also think of it even without writing. That means A1 plus A2 means it becomes 3(1) over minus 1 square. So 9/1, if it is maximum to minimum, or minimum to maximum is 1:9. Like this, you can think of. Because you know the time is not given like in the main examination. In the main examination, you have sufficient time to show the detailed of calculation. Remember, in the main examination, you are expected to show the detailed steps. You have to write down the formula, substitute the values, and you have to show at least 1 or 2 steps of simplification. And finally, you have to write down the answer along with the units. If you miss writing the unit, you lose the marks. But here, there is nothing like losing the marks for simplification. Other than you want only the correct answer. So how quickly you would be able to calculate. So your quickness is very important in any type of entrance examination, whether it is in CET, KCET, that is Karnataka CET, especially for the engineering, NEET, that is National Eligibility Test for the medical, related to medical entrance examinations, because you know that NEET is conducted at the all India level, and there the questions will be somewhat difficult compared to this, compared to our CET examination. And at the same time, you don't have sufficient time to think of and then calculating each and everything, and you have to do it quickly. And that is why you have to practice, and only if you practice it, you would be able to get it. Let us now come to the next question, that is question number 6. And in this question, in Young's double slit experiment, 2 slits act as coherent sources of equal amplitude A and of wavelength lambda. Oh, for lambda, it is taken as L. Okay, it is lambda, make it as lambda. In another experiment with the same setup, the 2 slits are sources of equal amplitude A and wavelength, it is lambda, but anyway, it is printed as L here, but are incoherent. So the ratio of the intensity of light at the midpoint of the screen in the first case to that in the second case. First case means coherent case, second case means incoherent. So in a coherent case, you know that the resultant amplitude becomes A plus A is equal to 2A. And remember, you can call it as I1 proportional to 2A whole square, because 2A whole square becomes, I'm just giving you only in brief. You may call it as I1. Instead of writing proportional, directly you can write I1 is equal to K, where K is a proportionality constant, 4A square. And I2 incoherent means you have to take the square of the amplitude and then add it. That means you will take it as A square plus A square. It becomes 2A square. That means I proportional to 2A square, or rather you may call it as I2. I2 is equal to 2K into 2A square. You divide one by the other. I1 by I2 means K into 4A square. Because you know I told you that A plus A, because they are added, and whole square 4A square over 2A square. A square cancel, K cancels. You will get 2 by 1. That means it is 2:1. Therefore, the correct choice for this question, question number 6, in Young's double slit experiment, it is 2:1. So now let me come to question number 7. Question number 7 is, how is the interference pattern affected if the Young's experiment was performed in still water than in air? Why it is called still water? Because when the water is flowing, then you will not have a perfect value like what you are getting in a still water. And that is why the question is given as still water. So in this question, that means, when the velocity, when the light passes into the denser medium like water medium, the wave frequency remains the same, the velocity is less. Remember the formula like V is equal to F lambda or C is equal to nu lambda. So in the case of water, it is a denser medium compared to air, the velocity is less and frequency remains the same, correspondingly the wavelength becomes less. Because again, when you go for this interference pattern means, let us say beta is equal to lambda d by d. When lambda is small, naturally you will have fringes will be narrower. So you have narrower fringes. That is what you have in question number 7. Coming to question number 8, the question number 8 says that how is the interference pattern in Young's experiment affected? uh, affected if one of the slits is covered with a black opaque paper. So if it is covered with black opaque paper, it is something like what I told you even in the previous case. It is like a single slit diffraction. So this question number 8, that means slit is covered with a black opaque paper means even though there are two slits, one slit is covered with a black paper means the outcome of the slit is something like a single slit. When you have a single slit, you will have what is called diffraction pattern. That's what I told you. The central fringe is of maximum width and the peak is also maximum. That's why I told you that the central fringe or principal maximum, or even we say that primary maximum, is flanked by alternate dark and bright bands of decreasing intensity and decreasing width. And here the choices are there, but I will go directly to the fourth choice. There will be a bright central fringe bordered. What I use the word flanked by. In here, use the word bordered on both sides by fringes of decreasing intensity. You may even say decreasing width. So this is what question number 8 is similar to that of diffraction pattern. Now let me move on to the question number 9. What happens to the interference pattern if the two slits S1 and S2 in Young's double slit experiment are illuminated by two independent identical sources? Like what you have seen in the picture of a theory of fringes or the expression for the fringe width. I showed the diagram S1, S2 and also the screen. The screen is at a distance capital D. But the question here is, what happens to the interference pattern if the two slits S1 and S2 in Young's double slit illuminated by two independent identical sources? Means in order to get the coherent waves or coherent sources, we have to use a single source and two slits, identical slits. Only when we use two identical slits and if they are kept at the same distance from a single slit, then we will get the coherent waves or coherent, they are called the coherent sources. But if they are independent identical sources, they cannot be the coherent sources or they cannot produce the coherent waves, and naturally no interference pattern is observed. The choices given is the intensity of the bright fringe is doubled, the intensity of the bright fringes become 4 times, two sets of interference. No, all those things will not be there, and the correct choice becomes no interference pattern is observed. Some illumination may be there, but anyway, you don't get the interference pattern like bright and dark fringes. I told you that the dark fringes are bright and dark fringes, the fringe width is the same whether you take the bright fringe or the dark fringe in the interference pattern. So coming to question number 10, and that question number 10 here is, what is the reason for what the question says? Oh, yeah, question number. You have to read the same question 9, and if you read the question number 9 and then come back to question number 3. Anyway, in your entrance examination, it will not be given like what is the reason for your answer to question number 9, because there will be multiple question papers. Even though the questions are same, not the same number will be there for at least 4 persons. If the first person gets, let us say, A1, then fifth person may get some B1, something like that. So that is why they don't give the same thing like what I have given here. Instead of repeating the question number 9, it is given. If I read it correctly, what happens to the interference pattern? That is question number 9. If the two slits S1 and S2 in Young's double slit experiment, and then say what is the reason for your answer question number 9. If you just look at it, that question number 10 is, of course, here what is the reason? And there is no constant phase difference. I told you that in order to get the interference pattern, we should have the same phase or a constant phase difference between the two waves. Therefore, this is the condition. Remember, the fourth choice is the correct choice. There is no constant phase difference between the waves emitted by the two sources. Now I will move on to question number 11. Of course, this question number 11 takes some calculation. At least it will take you to 1.5 minutes. You cannot solve it just orally, or rather mentally. You have to take a pencil and paper and simplify this. The question says, in Young's double slit experiment, the intensity of light at a point on the screen where the path difference lambda, even here also lambda is missing. In place of lambda, L is there, K units. What is the intensity of light at a point where the path difference is, again, instead of lambda by 3, it is printed as L by 3. L being the wavelength of light used means lambda. In order to do that quickly, I will tell you the calculation part. I have given you there that relation between the phase difference and the path difference. Phi is equal to 2 pi by lambda. Here, the path difference is lambda, K units. What you will write? Phi is equal to 2 pi by lambda into lambda, because the path difference is lambda. Therefore, lambda cancels, phi is equal to 2 pi. And remember, in the vector addition, you have taken like the resultant amplitude is equal to A1 square plus A2 square plus 2A1 A2 cos theta. Or even you can write it as R is equal to square root of P square plus Q square plus 2PQ cos theta. So anyway, if you come back to this, I is equal to, you can write it as A1 square means I1, A2 square means I2, I1, I2 means you have to write under the square root. So you can write that I is equal to I1 plus I2 plus 2 root I1, I2 cos 2 pi. And cos 2 pi, it is cos 360 degree. Cos 0 or cos 360 degree is 1. And therefore, you will get it as I1 plus I2 plus 2 root I1 I2. And you take it as I0 plus I0 plus 2 I0. Same intensity you take. And in that case, you will get it as 4 I0. That means the resultant intensity becomes 4 I0. and thus you can write it as I naught is equal to, yes, k is equal to 4 I naught, or I naught is equal to k by 4 you can write. On the other hand, other thing it is given this, where the path difference is lambda by 3. Again you find out and call that as delta dash, or delta dash is equal to lambda by 3. You make use of the same formula like phi dash is equal to 2 pi by lambda into delta dash, and phi dash is equal to 2 pi by lambda into lambda by 3. So lambda lambda cancels, you have 2 pi by 3, and 2 pi by 3 means 2 into 180 by 3, it comes to be 120 degree. So cos 120 you can write either in terms of what is that called, cos of 180 minus 60. It comes to be, what is that, 2 pi by 3. 120, you will write it as cos of 180 minus 60. That means it is minus cos 60, which is equal to half. Therefore, I naught plus I naught 2 I naught minus half, and you will get it as I naught. Anyway, your final answer becomes k by 4. So lambda being the wavelength of light used. Now let me move on to question number 12. The question number 12 says that two coherent sources of intensity ratio, that is 100 is to 1, interfere. What is the ratio of the intensity between the maxima and the minima in the interference pattern? So choices are given. Anyway, directly I will go for the solution. You can write that I1 by I2 is equal to 100 by 1, or simply call it as 100. Anyway, 100 by 1 is nothing but 100. So I1 is equal to, what is that? You can write it as 100, I2 is equal to 1. Again, make use of the same relation like what I told you in the previous case. I is equal to I1 plus I2 plus 2 root I1 I2. That means 100 plus 1 plus 2 into 100 into 1 becomes 100. Square root of 100 is 10. Therefore, 101 plus 20, 121. On the other hand, minima means I dash is equal to I1 plus I2 minus 2 root I1 I2. And again, you will write I dash is equal to 100 plus 1 minus 20. And on simplification, you get 81. So you write I over I dash is equal to 121 over 81. Because you know, no calculator or no logarithmic table will be given to you in the entrance examination. Whatever may be the entrance examination, no calculator, and even your watch calculator is not allowed. And therefore, you have to simplify. You get it as I over I dash 121 over 81. The simplest simplification you can think of is make that 121 as 120, and in the denominator you make it as 80, because anyway you have to do it approximately here. So 120 by 80 means 0, 0 cancels, and 4, 3 times 12, 4 2 times 8, you will get it as 3 by 2. So answer becomes 3 is to 2. Therefore, the correct choice is 3 is to 2. So now I move on to question number 13. The question number 13 is, in Young's double slit experiment, the fringe width with light of wavelength 6000 angstrom. Normally it may be given in terms of nanometer, but still I have given that as 6000 angstrom. Sometimes, you know, the problem may be in terms of angstrom, and that's why I have also given that 6000 angstrom is found to be 4 mm. What will be the fringe width if light of wavelength 4800 angstrom is used? In fact, this is also a simple problem. What you can write quickly is like beta is equal to 4 mm. It's given. Lambda is equal to 6000. Angstrom, you leave it. You can just write only 6000. And beta dash equals what? And lambda dash, you can write it as 4800. I could directly write beta dash by beta equals lambda dash capital D over lambda capital D by D. Anyway, the geometry of the experimental arrangement remains the same. Therefore, capital D and small d cancels both in the numerator as well as in the denominator. Therefore, we can write beta dash is equal to beta into lambda dash by lambda. Again, I repeat, you write beta dash is equal to beta into lambda dash by lambda. Beta is given, you call it as 4, and lambda dash is given as 4,800. Lambda is given as 6,000. You cancel those two zeros. You have 48 over 60. And if you simplify quickly, it comes to be 3.2. So it is, answer is B. So for question number 13, the choice is second one, that is 3.2 millimeter. And question number 14. In question number 13, again it will be repeated like this. Anyway, the detailed question will be given in the examination. And what will be the fringe width using light wavelength of 6,000? Entire apparatus is immersed in transparent liquid of refractive index. 4/3 means it is the refractive index of water. And remember, like what I have already said in the beginning, other question, like V is equal to F lambda. V is less, lambda is less. But anyway, you have to take the refractive index, and refractive index is N is equal to C by V. And C means you write it as F lambda, that is in A, and V is like lambda dash. FF cancels because the frequency remains the same when light passes from one medium into another medium of different refractive indices. Anyway, you will get 4/3 is equal to lambda over lambda dash, or lambda dash is equal to 3/4 lambda, and you just simplify, you will get that as 3 mm. So the answer, this is a standard question. You find this question in almost all entrance examinations and including in our main examination. So in our main examination also, these problems are very, very common, and I have given the numerical problems at the end, and object simply thinking or thought-provoking questions in the beginning. So now, anyway, for question number 14, the correct answer is 3 mm. And let me move on to question number 15. That question number 15 is what the question says. In Young's double slit experiment, the slits are separated by 0.28 mm. Remember, it is given in mm, millimeter. Here, all units are mixed up. 0.28 millimeter is given. Screen is placed 1.4 meter away. That is given in meter. The distance between the fourth bright fringe and the central bright fringe is measured to be 1.2 centimeter. This is given in centimeter. So all the three, millimeter, meter, and centimeter are given. You have to convert into the same unit, only then you get the unit properly. Otherwise, if you substitute as it is, then you don't get the answer at all. So you have to write what is that? That first one is the screen is placed one, that is all right. The distance between the fourth bright, fourth means you may call it as yn is equal to n lambda capital D by D, or y4 is equal to 4 lambda D by D. Then central fringer means you may take it as y0, 0 it is. Y4 minus y0, you can write it as 4 lambda D by D. So after writing it, if you simplify, yeah, what is given here is the measured, what is that? The fringe and the central bright fringe is measured. That means y4 minus y0 equals 1.2 into 10 raised to minus 2, because it is given in centimeter. Better you convert that into meter rather than centimeter, because the distance capital D is given in meter. Therefore, better you convert that into meter everything. So 1.2 into 10 raised to minus 2 equals 4 into lambda, and capital D is 1.4, and over small d, and that small d, you see here, slits are separated by 0.28 millimeter. It is millimeter. When you convert that into meter, it becomes 0.28 into 10 raised to minus 3. And simplify carefully. When you simplify that, it comes out to be 600 nanometer. So this is what I have taken only for sample few questions. It doesn't mean that only with these few questions you are able to understand, because naturally wave optics means it requires at least 8 to 10 hours to complete the entire thing. In 1 hour, whatever is possible, I have done that too only for the interference part. Interference, rest of the things we will have to. Okay, thank you. And now, in case if you have any questions to be asked or any comment to be passed on, please do that. I welcome you to ask your doubts or questions. Thank you. Sir, I think
Thank you, sir. So,
I think I have completed on time. Yes.
yes, sir. Chat box ಅಲ್ಲಿ ನಾನೇ ಒಂದು ಕ್ವಶನ್ ಇದು ಮಾಡಿದ್ದೀನಿ ಸರ್. How does the angular separation of interference fringes change in Young's experiment if the distance between the slits is increased?
ಸರಿ ಗೊತ್ತಾಗಲಿಲ್ಲ. ಇನ್ನೊಂದು ಸರಿ ಹೇಳಿ. How does?
ಆ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಇದೆ ಸರ್. How does the angular separation of interference fringes change in Young's experiment?
Angular separation means beta proportional to theta ಅಂತ ಬರ್ಕೋಬೇಕು ಅಂತ ಹೇಳಿ. Yes, beta proportional to theta.
Okay.
Beta proportional to theta means you have to talk in terms of theta, the angular separation.
Okay.
And theta is again we write in terms of lambda d by d. That's how we put it.
Okay, sir.
ಅದು ಸ್ವಲ್ಪ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿಕೊಂಡೆ ಸಿಂಪ್ಲಿಫೈ ಮಾಡಬೇಕು.
Okay, sir.
It is, of course, in place of theta, we write it as theta. Beta theta hakonಡ್ರೆ we get it.
Okay, sir.
Okay, sir. Next.
And one more, state the reason two independent sources of light cannot be considered as coherent sources.
Yes, two independent sources means the phase will not be the same for both of them. You know, basically the phase means the state of vibration. Yeah, phase difference means it is the time elapsed or the time difference between the two. However, let us say you are having two bulbs. ನಾನು ಒಂದು ಸಿಂಪಲ್ ಎಕ್ಸಾಂಪಲ್ ಕೊಡ್ತಾ ಇದ್ದೀನಿ. ಎರಡು ಬಲ್ಬ್ ಇದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ಎರಡು ಸ್ವಿಚ್ ಇದೆ ಪಕ್ಕದಲ್ಲೇ. ಎರಡು ಸ್ವಿಚ್ ಎರಡು ಬಲ್ಬ್ ಸಪರೇಟ್ ಆಗಿದೆ. ಯಾಕಂದ್ರೆ ಬಲ್ಬ್ಸ್ ನ ಸೀರಿಯಲ್ ಆಗಿ ಕನೆಕ್ಟ್ ಮಾಡಲ್ಲ, ಅಥವಾ ಸೀರೀಸ್ ಅಲ್ಲಿ ಪ್ಯಾರಲಲ್ ಆಗಿ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀವಿ. ಎರಡು ಸ್ವಿಚ್ ಹಾಕ್ಬೇಕು. ಎರಡು ಸ್ವಿಚ್ ನಮ್ಮ ಎರಡು ಬೆರಳಿಂದ ನಾವು ಸ್ವಿಚ್ ಆನ್ ಮಾಡಿದ್ರು ಒಂದಕ್ಕೂ ಇನ್ನೊಂದಕ್ಕೂ ಲೆಟಸ್ ಈಗ 4 ಫಿಂಗರು ಮತ್ತೆ ಮಿಡ್ಲ್ ಫಿಂಗರ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಂತ ಇಟ್ಕೊಳ್ಳೋಣ. ಯೂಶುವಲ್ ಆಗಿ 4 ಫಿಂಗರ್ ಸ್ವಲ್ಪ ಮೊದಲು ಹೋಗುತ್ತೆ, 4 ಫಿಂಗರ್ ಮಿಡ್ಲ್ ಫಿಂಗರ್ ಆಮೇಲೆ ಹೋಗುತ್ತೆ. ಅಂದ್ರೆ ಇದು ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಫ್ರಾಕ್ಷನ್ ಆಫ್ ಎ ಸೆಕೆಂಡ್. ಯಾಕಂದ್ರೆ ಮಿನಿಟ್ಸ್ ಅಲ್ಲಿ ಡಿಫರೆನ್ಸ್ ಬರಲ್ಲ, ನ್ಯಾನೋ ಸೆಕೆಂಡ್ ಇರ್ಬೋದು. ವಾಟ್ ಎವರ್ ಮೇ ಬಿ ದಿ ಟೈಮ್ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ಒನ್ ಅಂಡ್ ದಿ ಅದರ್, and that time difference leads to the phase difference. If there is a phase difference between the two waves, naturally we are not able to get the constructive and destructive interference, or the superposition is erratic, not regular. ಹೀಗೆ ಹೇಳ್ಬೋದು. ಆಮೇಲೆ ಸರ್.
Okay, thank you, sir.
Oh, thank you, sir. Thank you very much for all your encouragement. And I thank again everyone in the department, KSTA, and especially the chairman and the CEO. So my heartfelt thanks to all of you to give me an opportunity to interact with the students. In case if the students have any more questions, they can you can give my mail ID. I think like what you did last time, you collect those questions. In case if there are some more questions, definitely I will answer them. Thank you, sir.
Yes, sir. Okay, sir. Later on, I sent through a mail, sir.
Okay then. Okay.
Okay. Anyway, thank you, sir. Today we have to give a wonderful informative talk on wave optics.
Oh, thank you, sir. Thank you.
Is using several examples and several calculations of the different types of derivations. ಸೊ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡಲ್ಲೂ ಕೂಡ ಸುಲಭ ಮತ್ತು ಸರಳವಾಗಿ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಆಪ್ಟಿಕ್ ವೇವ್ಸ್ ಅಂದ್ರೆ ಅಂತ ಅನ್ನೋದನ್ನ ಸುಮಾರು ಎಕ್ಸಾಂಪಲ್ ಅಂದ್ರೆ ಪ್ರಸ್ತಾವನೆಗಳ ಮೂಲಕ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ ಸರ್. ಒನ್ಸ್ ಅಗೇನ್ ಐ ಥ್ಯಾಂಕ್ಫುಲ್ ಟು ಯು ಸರ್.
Thank you, sir. Thank you.
On behalf of KST and myself, once again thank you sir.
Thank you very much, sir. Thank you.
ಸೊ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಾಜರಾಗಿದ್ದಂತಹ ನನ್ನ ಎಲ್ಲ
ಇನ್ನೊಂದು ಕಳಿಸ್ಕೊಡ್ತೀನಿ. ಇಲ್ಲೆಲ್ಲೋ ಲ್ಯಾಂಬ್ಡಾ ಎಲ್ಲ ಮಿಸ್ ಆಗಿದೆ. ಅದನ್ನ ನಾನು ಇನ್ನೊಂದು
ಉಪನ್ಯಾಸಕರಿಗೂ ಕೂಡ
ಆಮೇಲೆ ಸ್ಟೂಡೆಂಟ್
ಧನ್ಯವಾದಗಳು. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.
ನಾನು ಆಮೇಲೆ ಕಳಿಸ್ಕೊಡ್ತೀನಿ ಅದನ್ನ ಇನ್ನೊಂದ್ಸರಿ ಚೆಕ್ ಮಾಡ್ಬಿಟ್ಟು. ಓಕೆ ಸರ್.
ಒನ್ಸ್ ಅಗೇನ್ ಐ ಥ್ಯಾಂಕ್ ಯು. ಓಕೆ ಸರ್. ಓಕೆ ಪ್ಲೀಸ್
ಸರ್. ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು.
ಥ್ಯಾಂಕ್ ಯು. ಸೊ ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಬಸವರಾಜ್ ಸರ್ ಅವರು ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಇಂದಿನಂತೆ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ವಿದ್ಯಾರ್ಥಿಗಳು ನಮ್ಮ ಸಿಸ್ಕೋ ವೆಬ್ಎಕ್ಸ್ ಮುಖಾಂತರ ಆ ಲಿಂಕ್ ನ ಉಪಯೋಗಿಸ್ಕೊಂಡು ಹಾಜರಾಗಬೇಕು ಅಂತ ಮತ್ತೊಮ್ಮೆ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಥ್ಯಾಂಕ್ ಯು.
ಓಕೆ ಸರ್. ಥ್ಯಾಂಕ್ ಯು.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.